Billions of years ago, when our galaxy was still young, something so violent happened that it changed everything around it. A giant star, bigger than 1,000 suns combined, exploded with a force we can't even imagine. The light from this explosion traveled for thousands of years through space, carrying secrets about how the elements that form our own bodies were born. Pieces of this dead star flew across the entire galaxy, creating colorful gas clouds the size of entire solar systems. But here's what keeps scientists up at night. This explosion wasn't like the others we know. It was so powerful that it broke all the rules we thought we knew about how stars die. What if this mega explosion was necessary to create the perfect conditions for life to exist? Subscribe to the channel, leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. Have you ever wondered what the Milky Way was like before the Sun or Earth existed? Imagine a time so distant that not even the sun was shining in the sky and there were no planets anywhere. The Milky Way was a very different place back then. It was large and quiet, filled mostly with simple things that are hard to see, like gas and very tiny bits of dust. If you could float through space at that time, you would not find any signs of life, no green plants, no blue oceans, and no rocky mountains. There were no planets at all. There was just emptiness with floating gas and clouds made from tiny particles. Back in this early age, the Milky Way had mostly only two types of gas, hydrogen and helium. These are the two lightest and simplest things that make up matter in the universe. Hydrogen is what makes water, and helium is the same gas that goes into balloons. But at that time, these gases were all alone in space. There were no other kinds of substances in large amounts. Atoms like carbon, oxygen, iron, and others, these are the building blocks that make rocks, water, and even living things, were almost missing. They were found only deep inside stars, trapped by the strong forces there. You might ask if all the things around us like trees, rivers, rocks, and even our own bodies are made from these special elements, where did all those elements come from? At that early moment, they were not yet free in space. They were missing from most of the Milky Way. If you could take a spaceship and look for somewhere just like Earth, you would never find it. The ingredients for life and planets were not available. The Milky Way did not have the same spiral arms you can see in pictures today. Its shape was more like a rough cloud, without clear circles or patterns. The galaxy was not as bright or colorful as it would later become. Stars were shining in some places, but there were many dark areas where the gas was thin and no stars had formed yet. Sometimes, in the thicker parts of the gas cloud, a few stars would start to form because gravity began to pull the gas closer together. Most of these early stars were simple and did not make many new elements. They lived their lives quietly and did not spread their material very far. The young Milky Way was like a bakery with only flour and water, but no sugar, salt, or any of the special flavors you need to bake different kinds of bread. The simple gas was everywhere, but nothing else could be made without something extra. The galaxy was waiting for a big change, something that would add new and important ingredients. There was much less happening in this early Milky Way than what we see today. There were no planets moving around stars, no comets shining as they passed the sun, and nothing living on any world. Even the light from the stars was not as rich as it is now, because the stars did not have the special elements that make them shine in different colors. The galaxy's story was just beginning, and it was missing many important chapters. But what was this gas, and why was it so important? Hydrogen and helium were made a long time ago, not in the Milky Way, but soon after the universe itself began. After the Big Bang, the universe cooled down and made these two gases. For a very long time, almost all the matter in the universe was hydrogen and helium. When galaxies like the Milky Way first came together, they collected huge clouds of this gas. The Milky Way started as a large collection of these clouds, slowly spinning together under the pull of gravity. Inside some of these clouds, gravity pulled the gas closer and tighter until it became so thick and hot that new stars started to shine. When stars form, they are like factories that can take simple atoms and join them together to make bigger and more complicated ones. But in the early Milky Way, only the very first stars were shining. Each star took millions or even billions of years to make new elements. This process was slow, so the galaxy stayed simple and empty for a long time. In these first days, there was nothing to see except stars and gas. There were no nebulae filled with colors, no asteroids, no planets covered in water, and not even any moons. The space was wide open and silent. If you could look with your own eyes, there would be mostly blackness, with tiny points of light from the oldest stars. These earliest stars were very big and heavy. Because they were so large, they used up their fuel very fast and did not live as long as smaller stars like our Sun. Most of them burned out quickly, at least quickly in the language of stars. Some lasted only a few million years. When they died, they sometimes exploded in flashes of light and energy that were brighter than anything else around them. But even with these explosions, there was still not enough of the special elements made to fill the Milky Way. These big stars tried to make new stuff in their centers. In their hearts, they squeezed small atoms together and made new elements like carbon and oxygen. But these elements stayed deep inside the stars, trapped until the star reached the end of its life. When a heavy star died, it sometimes released these elements, but in the early galaxy there were still not many stars and not many explosions. This means that for a very long time, the Milky Way did not have the right things to make planets, rocks, or life. All the special elements needed for these things were locked inside stars. The galaxy was waiting for something to happen that would change everything. Without these needed materials, planets could not stick together. Rocky planets like Earth or Mars need things like iron and silicon, but those did not exist yet outside stars. Even the dust floating in space was made almost only of hydrogen and helium, which cannot make solid ground or mountains. Without oxygen, there could not be any water. Without carbon, there could not be any life. You can imagine this time as if you had a large kitchen but no real food to cook. You have water and oil, but nothing to give taste or color. The Milky Way was like that, a giant space with lots of hydrogen and helium, but no real chance to create something different and interesting. Life, as we know it, could never happen in a place like that. So, what made things start to change? Over time, some of the big first stars exploded. When these stars ended their lives, they could send their new elements out into the Milky Way. But even then, this process was slow and did not make a big difference at first. It would take an event much bigger, a truly massive explosion, to finally spread enough new elements across large parts of the galaxy and bring about a real change. This early phase of the Milky Way was a time of waiting. It was a period when the galaxy was gathering its strength, collecting gas, and making its first few stars. But the real magic, the change that would allow planets and living things to one day exist, had not happened yet. The galaxy was like a sleeping giant, quiet and patient, holding simple gases, dreaming of what it could become with the right materials. It is important to remember how different this early Milky Way was from what we see now. Today, when you look at the night sky, you can see many colors and types of stars. You know that our own solar system is full of planets, some rocky, some made mostly of gas. There are moons, rings around planets, comets, asteroids, and even the dust that gives us shooting stars. All of this was missing in the early galaxy. There was only the silence of empty space, filled with very simple gas and just a few points of starlight. Over millions and millions of years, the gas clouds in the Milky Way shifted and moved. Sometimes, small parts of these clouds bumped into each other and became thick enough to form new stars. Each new star that was born had a chance to add more elements to the galaxy as it lived and died. But for a long time, these additions were small and slow. Because hydrogen and helium make up most of the universe even now, you might think nothing really changed. But when you look at Earth's mountains, oceans, and living creatures, and even at the metal in your phone or the water in your glass, you are seeing the proof that something did change. All these things are made from special elements that were missing at the beginning. The early galaxy was still a mystery for scientists. We cannot travel back and see what it was like, but we can use telescopes to study old stars and the light that has traveled for billions of years. Scientists have learned that the oldest stars are very poor in things like carbon and iron. This matches the idea that these elements were not free in space yet. These first stars had only hydrogen and helium to use, so they could not form planets with rocks or water. Slowly, as some stars ended their lives and exploded, the first small amounts of new elements got mixed into the clouds. Still, there were no big clouds filled with many elements. The galaxy was still waiting, still almost empty and simple, with just a hint of the changes to come. If you ever hear people say, "We are made from stardust," this is where that story really begins. It starts in a galaxy so old and so empty that you could never find a planet or a person there. All around was dark and cold, with nothing solid to stand on. In this silence and emptiness, the first steps of the universe's long story were taking place. The Milky Way, in that moment, was only a promise for the future. Every star that shined in that early time, every cloud of gas, every hint of light in the darkness was part of this beginning. But none of them could make the world as we know it. Life needed something extra, something to start making the special ingredients for water, rocks, and even bones. In this early Milky Way, those things could not yet even be imagined. The story of the Milky Way at this stage is about patience and waiting. It is about the galaxy holding on to its simple ingredients, slowly growing and preparing for the moment when everything would change. This moment was coming, and when it arrived, it would fill the galaxy with new elements and new possibilities. The early Milky Way was not ready for planets or life. But the first stars and clouds were only the beginning of a much bigger adventure. At the heart of this story is the simple truth. Nothing that you see on Earth, nothing you are made of, could have existed then. The galaxy was missing almost everything you see around you today. The long journey from that empty beginning to the rich and varied universe we now know all started here, in this quiet and simple Milky Way, waiting for its transformation. In the wide quiet of the early Milky Way, there was only the gentle movement of gas and dust. No planet-circled suns, and there was no place yet for oceans, mountains, or living things. The galaxy was waiting, holding its simple clouds of hydrogen and helium. But change was coming. It began with the birth of a giant star, one much bigger and heavier than the Sun we know today. In those old times, the gas in the Milky Way sometimes came together under the force of gravity. When enough gas and dust crowded into one place, they pressed together and grew hotter. This pressing happened over a very long time, not just years or centuries, but millions of years. As the gas became dense in some places, new stars were born. Most were small or medium in size, but in a few rare places, a much larger star began to form. These giant stars were special from the very beginning. When a giant star is born, it needs an enormous cloud of gas. This cloud must be much larger and heavier than the ones that make normal stars. When such a huge cloud comes together, it produces a star that glows much brighter and hotter than most others. From the first moment of its life, a giant star stands out by how much light and heat it gives off. It lights up the area around it, making it much easier to spot from far away, even in the dark galaxy. A giant star is made from the same basic gases as any star. It starts with hydrogen at its center, packed very tightly. The pressure and heat become strong enough that the atoms inside the star start to join together. This is called fusion. When fusion happens, energy is given off, and this energy powers the star. It makes the star shine and keeps it from falling in on itself. Inside a giant star, fusion works very quickly because of the huge size and the powerful gravity pushing down on its center. The star is always using up its hydrogen, changing it into other elements through fusion. Every second, millions and millions of atoms are joining together and making new things. This is not a slow or quiet process. The star grows brighter and burns through its fuel very fast compared to smaller stars. As time goes on, the star changes. The hydrogen in the middle of the star starts to run out. The star does not die right away. Instead, it finds a new fuel to burn. It starts fusing helium, and then, as time passes, it makes even heavier elements like carbon, oxygen, and eventually iron. The star's core becomes layered, with different elements being formed in different places. The deeper you look, the heavier the elements you find. Each layer inside the giant star is very hot and under great pressure. Fusion keeps going, building more complex elements as long as there is enough energy. These elements, like carbon, oxygen, calcium, and iron, are the same materials we find later in rocks, in water, and even in our bodies. But at this time, they are still stuck inside the star, locked away and held tight by gravity. The outside of the giant star looks calm, but the inside is always changing. The fusion reactions happen in the center, and this energy moves to the surface, making the star shine. On the outside, the star sends out light and heat, which travels across space. Around the star, there might be small clouds of gas made from bits pushed out by the star's powerful winds. Life for a giant star is very different from life for a small star. A giant star burns so brightly and uses its fuel so quickly that it cannot last very long. While a small star can live for tens of billions of years, a giant star lives for only a few million years. To most, a million years seems like a long time, but in the life of the galaxy, it happens very quickly. Through those millions of years, the giant star keeps changing. It grows larger and brighter. Sometimes, its outer layers expand, making it look even bigger. The winds coming from its surface grow stronger, pushing out some of the star's gas into space. Even with this loss, the star stays massive and powerful. The core at the center of the giant star continues its work, fusing lighter elements into heavier ones. At first, hydrogen becomes helium. When the hydrogen is almost gone in the core, the star moves on to fuse helium into carbon and oxygen. Later, it can even make neon, magnesium, silicon, and finally iron. Each new step takes more energy, and the time spent on each is shorter than the last. Iron is the last element the star can make through fusion in its core. This is because turning iron into something heavier does not produce energy. Once the core is filled with iron, the giant star cannot get any more power from fusion. At this point, something special is about to happen. The iron core grows as the star keeps fusing around it. It becomes heavier and heavier. Gravity presses down hard on the core, and the pressure gets higher every second. There is nothing left to release energy and hold up the weight. The balance is about to break. The inside of the star can no longer keep up with the heavy pressure, and it is getting close to the end of the star's life. During this time, the outer layers of the giant star are still sending out light. To anyone looking from far away, the star shines even brighter than before. If there were any planets nearby, they would be bathed in strong light and heat. But no planets like Earth could exist in this early Milky Way. There were no rocks, no water, only gas and tiny bits of dust made by the star and spread into space by its strong wind. Inside, more and more of the star's gas is turning into heavier elements. The star's center is getting close to a limit. The forces inside are growing too strong for fusion to balance. The star is under stress, waiting for a moment when it will no longer be able to hold together. The life of this giant star is not quiet or gentle. Because of its size and power, the star has a very active life. It changes color, shifts in brightness, and throws out gusts of gas into space across its short life. Its winds can travel very fast, far faster than any wind on Earth. These winds carry away some of the star's material, making the area around the star richer in elements than before. As the star nears the end of its life, the changes inside it happen even faster. The time spent burning each type of fuel becomes shorter and shorter. The layers inside the star become thin shells, each making a different kind of element for a brief time. The iron core keeps growing, and the star becomes more and more unstable. Many scientists believe that stars like this were very important for our galaxy. The new elements created inside them, that is, the carbon, oxygen, magnesium, silicon, and iron, were needed to let planets and life begin later on. But these elements could not help the galaxy as long as they stayed inside the star. They needed to be released into space. While the star burns brightly, a lot of its energy travels out into the Milky Way. This energy can push on the gas and dust around the star. Sometimes, if there are other small clouds nearby, the energy from the star might help squeeze these clouds and make them start to form new stars. In this way, a giant star can help make the galaxy a more active place. But the end of the giant star's life is different from any changes that come before it. The iron core is the key. Once it becomes too heavy, it starts to fall in on itself. The center of the star collapses in a very short time, less than a second by our counting. This is the first step in the star's final act. The collapse triggers an enormous release of energy, far bigger than anything the star has done until now. As the center falls, the outer layers of the star hit the core and bounce back. This makes a huge shockwave that moves outward. The shockwave blows away the star's outer layers in a powerful explosion. This event is called a supernova. For normal big stars, a supernova is already a very strong event, but sometimes something even greater happens, as scientists believe did in this early Milky Way. In the brief time before this explosion, all the heavy elements made during the giant star's life still wait inside, ready for release. They have quietly built up over millions of years, locked away and unseen by anyone looking from outside. Everything is in place for one of the galaxy's biggest events. This moment in the life of the giant star is not only the end of the star itself, it is the beginning of great changes for the galaxy around it. The star's explosion will not just spread light, it will throw all these special elements out into space. The gas and dust that were once part of the star will now mix with the wider galaxy for the first time. The changes that come from the explosion will reach far. The blast will send waves of energy that move through space, shaking the gas clouds in the Milky Way. The materials made in the heart of the star, carbon, oxygen, iron, and more, leave the broken star and join the galaxy's inventory of elements. This is the process that fills the Milky Way with the things needed to make planets, water, rocks, and all living things. Sometimes, if a star is big enough, the explosion is even stronger than a normal supernova. Scientists think that in this special time at least one giant star ended its life in a way that was much brighter and more powerful than usual. This single event would have thrown out enough new material to change large parts of the galaxy. When we look at the night sky today, we can see that the Milky Way is rich in different elements. This could only happen because giant stars like this formed, lived, created heavy elements, and died in these big explosions so early in our galaxy's history. The work of one giant star, making new elements and sending them out to the galaxy, made it possible for rocky planets to form much later. The life of a giant star, then, is not just about one bright body shining in the galaxy. It is about the story of how the galaxy collected the things it needed for the future. The giant star does its work in silence until the end, when it changes everything with a single explosion. After so many years of the Milky Way being quiet and almost empty, this powerful end opened the way for new things to happen. Every piece of iron in our blood, every bit of silicon and calcium in our bones started in the heart of a star like this. Our planet, and every planet with rocks and water, came from these elements. Before the explosion, the Milky Way was missing these important building blocks. After it, they became part of the galaxy, ready for the next stage. The story of this giant star shows how galaxies change over time. They do not stay the same forever. In the beginning, galaxies may be quiet with just simple gases and a few stars. But when a giant star is born, lives and dies, it gives the galaxy something new and precious. The galaxy is never the same after that. The material and energy from the giant star's life and death are still moving through the Milky Way today. Scientists study the clues left by these events, looking at where new stars form, what elements they have inside them, and how the patterns of gas and dust were changed by old explosions. These clues help us understand that every star, no matter how big or small, is part of the long story of the galaxy. And all of this began with the quiet waiting of the early Milky Way and with the birth of a single giant star whose life and death would shape the galaxy for billions of years to come. With the death of the giant star, the Milky Way was changed in ways that had never happened before. The explosion at the end of the star's life was not silent or gentle. It was a powerful event that released more energy, more light, and more new materials than anything else that had occurred up to that moment. The quiet collection of gas and dust in the young galaxy was disturbed by an event that was stronger than a normal supernova. The entire area around the star was shaken. The remains of the star rushed outward at great speed in every direction, carrying with them all the special elements the star had created during its lifetime. This was not just an ordinary explosion. Scientists who study stars call explosions at the end of a star's life supernova. These are always impressive and powerful, but the event that happened with this giant star was even greater than most supernova. It gave off more light, more energy, and spread its contents across a much larger space. It was among the most powerful explosions that can happen in a galaxy like ours. As soon as the star's heart could no longer hold the pressure from the heavy iron core, the core fell in on itself. This happened very quickly, in less than a second. When the center collapsed, the outer layers of the star crashed toward the middle. The clash caused a huge wave of energy, a shock wave. This shockwave pushed everything around it outward, blasting the gases and all the materials made in the star far, far into space. For a short time, this explosion was so bright that, if someone were watching nearby, it would have outshone all the stars around it. For a few days or weeks, the explosion gave off more light than the rest of the galaxy in that area. The light sped away from the center, traveling across the Milky Way, and making the area near the explosion much brighter than normal. Inside the enormous cloud sent outward, there were many elements that never existed free in space before. These were elements like iron, oxygen, carbon, silicon, calcium, and others. They are very important for the building of planets, water, rocks, and even living things. Until this event, these materials were locked away, deep inside the heart of the giant star. The explosion broke the star apart and released those elements for the first time. The pieces of the star moved quickly, racing into the emptier areas of space, mixing with the hydrogen and helium that had been there since the Milky Way began. The amount of energy released by this explosion was huge. It was much more than just light. The energy spread through space as fast-moving particles and strong waves. These waves of energy pushed and heated the nearby clouds of gas. The force of the blast could even move or squeeze clouds that were far away from where the star once shined. This explosion had a shape that was special. Instead of making a small ball of high-speed gas, the powerful shockwave pushed matter out in every direction, making a very large area of hot, ionized gas. The explosion did not stop quickly. Its effects carried on as the new elements mixed with the clouds and dust already wandering through the Milky Way. Scientists know that supernova explosions can release huge amounts of matter. But the explosion of this giant star, sometimes called a hypernova, when even stronger than normal, sent out more energy and more new elements than almost any other star death. Its effect reached large areas, and the fast-moving gas cloud covered a big part of the early galaxy. The elements created in the giant star's core were not released in simple, equal amounts. The explosion mixed them in new ways. There was more of some elements, like oxygen, and less of others, making the pattern of materials from this blast different from what is seen in most other supernovae. If scientists study gas clouds that have this unique mix today, they can tell that a big special explosion happened a long time ago. As the newly freed materials raced outward, they began to meet clouds of hydrogen and helium. These clouds absorbed and mixed with the fresh, heavy elements, making parts of the Milky Way richer and more complex than before. The clouds glowed from the heat and the energy of the explosion, shining with new light. Sometimes the explosion itself made new light and heavy elements at the moment of the blast, adding even more to the cloud. While the main explosion only lasted for a short period, its results lasted for millions of years. The hot, bright cloud from the super-powered explosion slowly cooled and stretched out. It moved farther from the site of the star's death with every year. This cloud was less dense than it had been in the star, but now it was full of building blocks never before seen outside of stars. The shockwave from the explosion carried energy for a long distance. This energy was powerful enough to shake and compress some gas clouds that had been floating quietly for millions of years. In the places where the shockwave passed, it sometimes started new changes. If a gas cloud became compressed, it might begin to get thicker and hotter, and in time, a new star could be born. In this way, the powerful death of a giant star helped the galaxy change. It started processes that would much later lead to the birth of new stars, new systems, and one day, new planets. Nothing had ever spread these special elements so far and so fast in the Milky Way. Before this explosion, almost all the matter in the galaxy was simple. Afterwards, huge areas of the Milky Way were richer in carbon, oxygen, iron, and other vital materials. These elements were now free to join with the clouds and dust all around. Every new place they reached was changed by their presence. Scientists spend years studying the traces left by ancient explosions. They use special tools and telescopes to look at very old gas clouds in space. Sometimes they can look at the light that comes from these clouds and tell what elements are inside. When they find unusual amounts of certain elements, like more oxygen or iron than expected, they know that a massive, special explosion must have happened in the distant past. The explosion did not just change the materials in space. It also made new patterns in the way gas and dust were spread out through the Milky Way. By pushing some clouds together and making empty holes in others, it helped shape the galaxy's arms and the spaces between. If you could see the galaxy from far away, you would notice areas made brighter and thicker by the debris from the explosion. As time passed, the gas and dust hopped from place to place, moving gently on the currents made by the Great Blast. Some of the debris slowly became cooler and began to gather in bigger clouds. These clouds were much more complex than before. For the first time, they had all the important elements needed to make the surfaces of planets, the water found in oceans, and the materials for life to begin. The shockwave traveled for a very long time, sometimes for millions of years, before it became weak. Even after the energy faded, the effects were not lost. The mix of elements stayed in the clouds, ready to become part of something new. The light from the explosion was also special. It included bright colors and many kinds of light, even types of light humans cannot see with their eyes. By studying this light, scientists today can learn about the temperatures, the kinds of materials made, and even how fast the gas was moving. The fingerprints of the ancient explosion are written in the light coming from the old clouds. The remains of the explosion still exist in the Milky Way, though they have changed shape and spread out far from where they started. These remains form large clouds that scientists sometimes call supernova remnants. They are like patches or marks left in space, full of special elements. These clouds can stretch across great distances, many times wider than the distance from the Sun to the farthest planet in our solar system. No other event before this sent out so many new things all at once. All the materials that we find on Earth today, such as the iron in rocks, the calcium in bones, the oxygen in the air, and the carbon in living things, were made in stars. But they were only added to the Milky Way's gas and dust by explosions like this one. Without these huge blasts, the galaxy would have nothing but hydrogen and helium. No planets could form, and life would be impossible. The ancient explosion also helped create a more organized structure in the Milky Way. When the shockwave pushed gas aside, it made some areas empty and others more crowded. This began the first patterns that would later become the spiral arms seen in pictures of the galaxy. The force from the explosion is one of the things that helped the Milky Way stop being just a cloud of gas and start to become a galaxy with form and shape. The new elements raced through space after the explosion. They did not stay where the star died. Instead, they spread out over vast distances, joining with many other clouds. Sometimes the elements mixed so well that later clouds would contain materials from many different stars and explosions. In this way, every part of the galaxy started to share in the new richness given by the explosion. Other stars would form later from the clouds changed by the blast. These new stars, unlike the first ones, were made not just from hydrogen and helium, but also from carbon, oxygen, iron, and other crucial materials. The planets that formed around these newer stars could now be made of rocks, have water, and maybe even have all the ingredients for life. When scientists look at very old stars, they see the proof of this explosion. Ancient stars born before events like this do not have much carbon or iron. Stars that were born after the big explosion show signs of these elements in their light. This tells us the explosion truly changed the materials used for making new stars. The effects of the explosion reached farther than just the area around it. Its shockwave could travel across large parts of the Milky Way. In its path, old clouds were changed, crushed together, or swept aside. Empty spaces were made where once there were clouds, and in other places, new stars could begin because the clouds were squeezed and made thick enough for gravity to act. This one event became a turning point in the Milky Way's history. It made everything that came after it possible. All the things we see around us, planets, water, metal, and even the air we breathe, needed the elements that were made in the depths of the star and set free by its explosion. The Great Explosion was not an end, but a powerful new beginning for the galaxy. It took what the giant star had made over millions of years and sent it out to fill the emptiness between the stars. The ingredients for worlds, for oceans, for mountains, and for living things were now mixed into space, ready for the next steps in the galaxy's story. The Milky Way was no longer just a simple cloud of gas. It had become a place filled with new possibilities. From that moment on, every time clouds of gas moved and gathered, they carried with them small pieces of that first giant star. When a new star was born, some of the special elements from the explosion became part of that star and any planets that formed around it. The journey from simple clouds to rich and varied worlds had truly begun, all because of a single powerful explosion that changed the entire galaxy forever. As the special elements from the giant explosion drifted farther into the Milky Way, the galaxy could now change in ways it never had before. The space that was once filled with only simple gases now carried small but important pieces of matter that had been created by the giant star. These new building blocks did not stay still. Every cloud that picked up these elements was different from before. They carried the results of millions of years of work inside the giant star, and the power of the explosion had set them free. Inside the cloud of material, temperatures were very high just after the explosion. The atoms and particles were moving quickly. There was also lots of energy from the supernova's shockwave. This energy spread through the surrounding gas and dust, mixing the new elements in every direction. The shockwave caused some areas to be squeezed more closely together, and in other spots, it pushed the gas far apart, leaving emptier spaces. As time moved forward, this hot gas cloud began to cool. In the wide open spaces of the galaxy, heat escaped slowly, so it took millions of years for the cloud to lower its temperature. As it cooled, something special happened inside the cloud. The fastest moving atoms lost energy and began to slow down. The pieces of dust made from carbon, iron, and oxygen started sticking together. The cloud became less spread out and small clumps began to form. Some of these clumps, though still very small compared to the whole cloud, were rich with heavy elements. The carbon, oxygen, calcium, and other elements were mixed with hydrogen and helium. These groups of atoms were not arranged in any special way. There were many collisions as the particles moved and joined together, forming thicker patches of gas and dust. These patches were the first examples of places in the Milky Way with all the ingredients needed for new things. The explosion had done something more than just spread new matter. It also helped stir up the Milky Way. The patterns of movement in the gas clouds changed. Some clouds moved faster, some slower. The direction of their movement shifted too. As a result, areas that were once far apart now moved closer together, and other areas were pulled apart. The galaxy was becoming more complicated and interesting. With every passing year, the mixture in the clouds slowly evened out. No longer was it just hydrogen and helium floating alone through space. Now, every cloud that took in the debris from the explosion carried the heavier elements. The clouds were still large compared to the size of any planet or star, but they were full of tiny, important particles. These particles did not go unused. In the future, they would become the building blocks of nearly everything solid in the universe. New types of reactions started inside the cooling clouds. Certain chemical changes could take place now that there were more elements available. Some particles stuck together to form small grains of dust. Other atoms combined chemically to form simple molecules, such as water or carbon monoxide. These chemical steps were needed before planets, and even life could come into existence. The heavy elements created in the giant star did not stay together. After the explosion, the high temperatures forced them apart. But as the gas cooled, gravity began to pull on the heavier parts more than on the lighter ones. Over millions of years, gravity caused the denser areas of the cloud to collect even more dust and gas. These areas became thicker than the space around them. As gravity worked on these thickening regions, the materials inside continued to mix and react. With each small pull, the denser patches became more stable and less likely to drift away. The cloud of dust and gas, now rich in elements, slowly divided into many pieces, some larger, some smaller. Each of these pieces held a little bit of the original matter from the exploded star. While some clouds were changed by the blast, others in the galaxy did not get touched. But the clouds that held the new materials became the most important for what would happen next. The special elements helped clouds cool faster and stick together more easily, helping gravity do its work. Gravity is the reason that gas and dust come together in space. When enough matter collects in one place, gravity can make it shrink tighter and tighter until it might start to form something new. Small grains of dust made from iron, carbon, and other heavy atoms helped this process. They acted as spots where the lighter gases could collect and cool down faster. As the thick clouds of matter continued to grow, their centers became the birthplace for even denser clumps. These clumps kept getting heavier as more material was drawn into them. This story of cooling, mixing, and clumping was repeated across many places in the Milky Way. With every supernova, the galaxy received more of these special elements, but the explosion from the giant star was one of the very first and the biggest. Before, clouds were just wandering groups of hydrogen and helium. Now, these clouds were truly different. They had all the ingredients for making things that never could have existed before. The cloud from the explosion spread out over huge distances, but it did not disappear. Even as some of it mixed into new clouds, small parts kept drifting through space for billions of years. Some of this material would never be part of anything big, staying as dust moving quietly in the galaxy. But in many places, the new elements became part of something large, something that could change the Milky Way forever. The chemical changes inside the clouds marked an important shift for the universe. The new atoms joined together in simple molecules, making the clouds able to cool more quickly. Cooler clouds shrink and become even denser. This made it more likely for stars and planets to form inside them. Before, with only hydrogen and helium, the cloud would not cool enough for this to happen. With carbon and oxygen joining the mix, clouds could grow cold, quiet, and thick, just the right conditions for gravity to create something new. These denser pieces of clouds would one day become nurseries for stars. In these special places, the gas and dust would be packed so tightly that the temperature and pressure would rise again. In time, new stars would begin to shine, carrying heavy elements right from the start. These stars, made in the next generations, were unlike the oldest stars, which had no heavy elements at all. The new stars were the first to have all the chemical building blocks that would one day help create planets, water, and even living things. Every atom that was created inside the giant star and sent into space by the explosion took a long journey. Some found their way into new dense clouds almost right away. Others moved through the Milky Way for many millions of years before finding a home. Each time a cloud collected more special elements, the mixture inside became a little richer and a little more ready to become something else. The explosion had even more effects. The waves of heat and pressure sent by the blast pushed on other clouds, creating many areas with high energy. These waves made clouds spin and tumble, helping gravity gather more matter in certain regions. Sometimes the waves made clouds break apart, but more often they created more places where new stars and new planets could begin. Over time, the Milky Way changed a lot. Instead of being a quiet space with nothing inside but simple gas, the galaxy became a busy place, full of moving clouds, bursts of energy, and the seeds for future worlds. The heavy elements continued to travel, touching every part of the galaxy with the promise of something new. The heavy elements were not spread equally everywhere. Some clouds got more iron and carbon than others. Some clouds were touched by the explosion's shockwave and became thicker right away, while others stayed thin and cold for millions of years more. But every time a new generation of stars formed, those stars mixed the galaxy even more, sharing heavy elements farther and farther. Today, when scientists look at the oldest stars and clouds, they can still find signs of these ancient events. In some places, more iron or more oxygen means those clouds once received dust from a giant explosion. In other places, the simple, empty clouds are reminders of the times before the stars gave their building blocks away. The elements set free during the explosion served as the base for all that would follow. When clouds cooled, shrank, and mixed, they could form not just new stars, but also the worlds that circled them. Before, this was impossible. Without iron and silicon, no rocky planets could be made. Without oxygen and hydrogen together, there could be no water. Without carbon and other special elements, life could never happen. Each piece of the material from the explosion was important. The iron in a rock, the calcium in a shell, the oxygen in a drop of water, all started as an atom made in a star and sent out by an explosion. When these atoms collected together in cloud after cloud, they built up what would be needed for planets, moons, comets, and everything else in the galaxy. The birth of new elements did not stop with that one explosion. Each time a star died and exploded, more heavy elements were made and spread out. But the greatest change came with the first, biggest explosion. It was the event that made the Milky Way ready for the next big step, the birth of new stars with all the right elements for the beginning of worlds. All across the Milky Way, the space between stars became filled with these heavy elements. The dust drifted, sometimes for many millions of years, finally falling into new clouds, mixing and becoming part of something greater. Each cloud carried its own special story, but all of them were changed by the material from the giant star's explosion. As time passed, the chemical changes inside clouds and the gathering of dust and gas continued. The Milky Way that was once empty and simple grew richer, more complex, and more interesting. There were now regions in the galaxy holding everything needed for stars, and for the first time, for the rocky worlds and water that are important for life. When new stars finally formed from these changed clouds, something important happened. The new stars had planets around them that were made from the material released in the explosion. These planets were rocky, with metals and other heavy elements inside them. The beginnings of worlds had arrived, shaped from the remains of a giant star, set free in a single, powerful instant. Every step in this long process, from the cooling of the gas to the forming of small clumps, to the birth of stars and planets, was made possible by the new elements born in the heart of the giant star and released by its explosion. The galaxy would never be the same after these changes. With every year that passed, the Milky Way became more complete. It held the seeds for stars, planets, oceans, and for the long journey to life. All the new stars and the systems that started to form would share in the same atom-filled clouds. The same materials moved again and again, collecting in planet cores, floating in oceans, and forming the air around future worlds. The long journey of the galaxy's matter had only just begun, but now it included everything needed for new kinds of beauty and new stories. The Milky Way, once simple and quiet, was now full of rich clouds and dust, ready for the next steps that would make the galaxy more than just a collection of stars. Clouds across the Milky Way now held the special matter formed in the heart of a giant star and spread by its powerful explosion. These clouds were no longer just empty or plain. They were full of many kinds of atoms and dust, moving together in wide, slow patterns throughout the galaxy. Each cloud was shaped by time and by the energy of the supernova. The movements and changes inside these clouds set the stage for everything that would happen next. The materials drifting inside these vast clouds included both the simple gases that had always been there, like hydrogen and helium, and the new elements such as carbon, oxygen, iron, and silicon. In the cold depths of space, these materials moved and mixed, gently bumping each other. Some combined to form tiny grains of dust. Others came together to make simple molecules like water and carbon dioxide. The clouds slowly became thicker and darker in some places, where dust blocked more of the light from the stars. As the dust and gases shifted, some patches within the clouds became more crowded. Gravity gently pulled the particles toward each other. Over millions of years, gravity kept pulling, making certain areas of the clouds denser and denser. Sometimes, a wave from another exploding star or a push from a moving cloud nearby sped up the squeezing of these clumps. When a clump got heavy enough, gravity compressed it tightly, making the center of the patch grow even denser. The denser parts of these clouds, where gravity was working most strongly, began to change more quickly. Deep inside, the temperature started to go up. The squeezing of the dust and gas made these centers heat up and glow. The light and warmth grew slowly, almost too weak to notice at first. With time, the thickest clumps inside the cloud became what scientists call protostars. A protostar is the beginning stage of a real star, still gathering gas, not yet shining bright. Around these growing protostars, much of the dust and gas continued to spin. Instead of falling straight into the center, these materials formed wide, flat disks stretching far out from the middle. These disks were thick with building blocks like iron, carbon, silicon, and others, all spread out in a big, slow ring. The new disks were full of material from the supernova, even though the explosion had happened millions of years before. The coldest, darkest parts of the clouds stayed far away from the protostar in the center. But closer in, the disk around each forming star was heating up. Inside these spinning disks, the heavy elements and dust began to stick together. Small bits attached to other small bits, slowly forming bigger and bigger lumps. The lumps grew each time they bumped and joined with other lumps. These new lumps became small rocks and then even bigger pieces called planetesimals. They were made of the same heavy materials that the giant star had thrown into space: iron, nickel, carbon, oxygen joined with hydrogen to make water, and much more. The early planetesimals moved slowly around the young star, sometimes colliding, sometimes passing by quietly. Sometimes two planetesimals crashed together and stuck. Each time this happened, they grew larger. In some places, these growing bodies became very large, turning into protoplanets. Over many millions of years, these protoplanets swept up more and more of the dust and rocks as they traveled in their orbits around the young star. When enough material was collected, these bodies grew large enough to become true planets. There were many disks forming across the Milky Way, in different clouds and at different times. Wherever the heavy elements from a supernova were present, rocky bodies and planets could start to form. The process was slow but steady. The dust that began as the final breath of a giant star was now being built into brand new worlds. Water became possible too. Before the supernova, there was not enough oxygen in the galaxy for water to form. After the explosion, clouds could gather enough oxygen to join with hydrogen in the coldest areas, making tiny bits of ice. When these ices became part of planetesimals and protoplanets, they brought water to the new planets. Water is needed for life, But water in space starts as tiny, cold grains, hidden in darkness before gathering on forming worlds. The largest new planets formed closer to the center of the spinning disk, where it was hotter. These planets carried big cores of rock and iron, built from the dust of the exploded star. In places farther out from each disk's center, some planets collected more ice and gas. The planets that formed here were bigger but lighter, made mostly of gas and ices that had not melted away in the warmth. Every planet that came together in these disks was different because the mix of building blocks was not the same in every place. Some planets became large and rocky, others small and covered with thick atmospheres of gas. But everywhere, the iron, oxygen, carbon, and silicon from the giant star were present. Over millions or billions of years, the results of these processes filled the Milky Way with many worlds of different sizes and kinds. Some planets stayed close to their stars, circling quickly in hot orbits. Some moved in wide, slow paths far from any warmth. Others were caught as moons, circling around larger planets. Still others stayed as smaller rocks, comets, or dust, never becoming part of a planet at all. The special mix of materials in every new planet determined what kind of world would form. When there was enough iron, planets could have strong cores and magnetic fields. With enough silicon and oxygen, solid ground could form. With water, ice, and carbon, there was a chance for rich soils and oceans. All these pieces came directly from the dust created during the life and explosion of a giant star. The spreading of the supernova dust through the Milky Way made almost every planet possible. Without iron, no planet could have a dense center. Without silicon or aluminum, there would be no rocks or mountains. Without water, there could be no oceans, lakes, or clouds. The life that would one day appear on planets like Earth would depend on all these parts being present, mixed well inside the clouds before the planets formed. Not every new star and disk was lucky enough to get the same amount of dust from the explosion. Some regions of the Milky Way still had fewer heavy elements, so planets there could be small, icy, or not form at all. But in the regions reached by the full force of the supernova shockwave, new stars could become mothers to full, rocky planets with all the riches the star's life had created. As new stars lived and died, the Milky Way changed. Every time a new giant star was born and exploded, more heavy elements mixed into the clouds. The number of rocky planets and planets with water grew. Some places in our galaxy became especially rich in the right elements for building planets like Earth. The weighing and shifting of these clouds and disks and the elements inside shaped how the Milky Way looked. Where gas and dust gathered thickest, whole families of stars formed together. They often created large groups called clusters. In these clusters, many stars of different sizes were born at the same time. Each star surrounded by its own disk, each disk making its own new planets and moons. The galaxy slowly filled with many types of worlds. Some new planets may have only been hot rocky balls with no water. Others could have cooled, held water, and kept thick clouds of atmosphere. There were also planets made mostly of ice, living far away from their stars in cold darkness. Everything depended on how much of the exploded star's dust and elements made it into each new disk and planet. In time, some of the matter from the exploded star would be part of comets, traveling on huge, cold paths around their stars for billions of years. These comets and icy bodies could later crash into new planets, bringing more water and carbon, further helping to make those worlds ready for more changes. Because the Milky Way had received such a big burst of new elements, the process of making planets and new stars became much more active after the explosion. Each round of new stars created more chances for heavy elements to collect and change the next generation of clouds. The galaxy began to look more alive, more full of color and structure, because the spreading clouds of dust carried light and gave shape to the spiral arms. The elements created in that early explosion are the same ones needed for life. Carbon is the key to all living things. Oxygen and hydrogen are needed for water. Iron and calcium are found in bones, blood, shells, and more. Every tiny grain of dust from the supernova contained the beginnings of these possibilities. Scientists today still find leftovers of these ancient clouds. When they point their telescopes at dark, cold parts of the Milky Way, they see the chemical fingerprints of those early elements. The pattern of heavy elements in the oldest stars and clouds lets them know how and where the building blocks for planets and life were made and spread. Even after billions of years, supernova debris still moves as dust, gas, and ice between the stars. Some of it will never change, always floating quietly. Some will, one day, join again in the forming of new stars and new planets, repeating the cycle again and again. The Milky Way continues to recycle the dust and atoms created long ago. The effect of the long-ago explosion can be seen everywhere. Every stone, every drop of water, every living plant or animal contains atoms that were first made in a hot, bright star and given to space by a supernova. The air we breathe and the ground we stand on come from these ancient clouds. Nothing in our world is untouched by the story of that explosion. The next big change in the galaxy would depend on what these new planets could become. Some would stay empty and lifeless, and others, under special conditions and with the right mix of elements, would someday support living things. But they all began as drifting atoms moving through cold, dark clouds, brought together by gravity and joined together by the long, patient work of time. As the dust from the explosion was rebuilt into new worlds, the Milky Way grew more and more interesting. Every time a new cloud thickened, every time a new disk formed, every time a tiny planetesimal joined with another, the story continued. All the materials needed for mountains, rivers, and trees first traveled through these dark clouds as the simplest dust, waiting for a chance to become part of a world. Now the Milky Way was changed forever. It was a galaxy busy with the making of stars, planets, moons, and more. It had grown from a quiet cloud of gas into a place filled with color, light, and the first hints of life's ingredients. The dust from one special explosion had begun a chain of events that would echo for billions of years, reaching from the oldest stars to every new planet and even to every living thing. The Milky Way was now busy, no longer silent or empty. Clouds full of dust and heavy elements kept moving across the galaxy, pulled by gravity, changing shape, joining together, and breaking apart. Every part of these clouds was made from the smallest bits of matter that, long before, had come out of exploding stars. Inside these clouds, new things kept happening. Matter did not stand still. Instead, it began to come together, creating new stars, and in many places, starting the long and careful work of making planets. As clouds floated in the cold of space, some became thicker than others. When gravity made one area of a cloud much denser, the gas and dust there slowly formed a clump. This clump got bigger as more material joined it. Over many millions of years, the clump grew heavier, pressing the gas and dust together in the center. As this pressure increased, the middle of the clump became hot. The energy in the center rose until it was strong enough for a new star to be born. The forming of a new star is a slow process. The cold, dark cloud pulls in more and more gas with gravity, getting warmer and spinning gently. The center of the cloud glows before the star itself is shining. Over a very long time, the pressure and temperature in the middle become high enough for a star to finally light up. In that moment, atoms in the center begin to join together and give off energy. This energy is the power of the new star, and it sends light and heat far out into space. The place where the star is born becomes bright and warm, a tiny sun shining in a once dark cloud. The cloud is not gone when the star is born. There is still lots of dust and gas spinning around the new star, spread in a wide, thin disk. This leftover material does not fall into the star, but instead forms a flat ring circling the center. Here, the process of building worlds can begin. Inside the spinning disk, different materials do different things. Close to the new star, it is very hot. Only tiny grains of rock and metal can survive here. Farther out, where it is colder, ice and other frozen materials remain whole. The first step is that dust particles bump into each other and stick, forming bigger and bigger pieces. The bits of dust become pebbles, then rocks, and finally bodies much larger than any mountain on Earth. As these rocks grow, gravity helps them keep collecting more dust and other rocks. Over millions of years, they sweep their paths clean, collecting what they touch. These new objects are called planetesimals. Some planetesimals grow so large that their gravity also starts to pull them into a round shape. When this happens, they become protoplanets. The largest of these may one day be full planets. Each new forming star has its own cloud and spinning disk, and so there are always many places in the Milky Way where new stars and planets are forming at the same time. Some disks may not have enough heavy elements to build rocky planets, but most, after the supernova, are rich in the iron, carbon, and oxygen brought to the galaxy by dying stars. These elements are mixed in the dust and rocks that make up all the new planets. Near some young stars, many large planets may form. In other places, only smaller rocky planets or groups of icy bodies appear. Some will have water because the oxygen from exploded stars can join with hydrogen to make ice. This ice, carried by small bodies, can then be delivered to planets closer to the new sun. Water becomes part of the planet's surface, forming oceans or lakes. With each new generation of stars and planets, the Milky Way changes a little more. Some old stars die and explode, sending even more heavy elements into the clouds. These explosions mix the ingredients for planets and life even better, so each new disk of dust and gas has a little more iron, a little more carbon, and a little more oxygen each time. On young planets, the heavy materials in their centers help them form a hard crust and, sometimes, a powerful magnetic field. These things can protect a planet's surface, letting it cool and keep an atmosphere. Carbon helps to build rocks and soil, while iron forms the planet's deep core. All of these ingredients began in the middle of long-dead stars. Not every planet is the same. In some parts of the galaxy, planets grow large and hold onto thick atmospheres. In other places, rocky planets are small and dry, or icy and cold. Some planets stay as gas giants with deep clouds and turbulent weather, while others remain small and airless. The mix of dust, ice, and rock in each disk decides what kind of world will appear. Even after a planet is formed, it continues to change for millions or billions of years. Some are hit by leftover rocks and icy bodies, which can bring more water and carbon. Some planets experience strong heating and cooling, making their surfaces crack and move, forming mountains, valleys, and seas from the inside out. All the things seen on Earth, such as mountains, rivers, oceans, and air, began as small pieces in a disk of dust and gas around a new sun. The heavy elements inside them were made in stars before the solar system existed. Pieces of exploding stars made the iron in Earth's core, the oxygen we breathe, and the carbon found in every living plant and animal. The pattern of new star and planet formation keeps happening all across the Milky Way. Some areas are always busy with the birth of new stars and worlds. In these regions, the clouds are thick with dust, and the newest stars can often be seen covered by glowing clouds of gas and dust lighting up the space around them. The leftover material that is not used in building planets and moons remains in the system as dust or small rocks. These often become comets, asteroids, or meteoroids. Sometimes they crash into young planets, helping to build their surfaces, bring more water, or heat them up with energy from the impact. Where the heaviest elements are most common, the planets that form are more likely to have rocky surfaces, strong cores, and even the possibility for seas or atmospheres. In places where the exploded star dust is less common, the planets that appear may not have all the things needed for life as we know it. Every atom of iron, oxygen, silicon, and carbon in a new planet once belonged to a star. The material can move from cloud to star, from star to planet, and from planet back into space over billions of years. Each time the galaxy becomes richer, changing little by little with each new cycle of birth and destruction. The solar system is an example of this process. It began as a cloud of gas and dust, full of atoms and grains made by earlier stars. Gravity pulled part of that cloud together, making the sun. Most of the leftover material spun around the sun in a flat disk. Dust and rock began sticking together, forming growing bodies. Over millions of years, these planetesimals joined to become planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and many smaller objects. Earth was made mostly from rocky material, and enough iron and nickel collected in its middle to form a dense core. Water, likely carried by icy bodies and dust, gathered on its surface. The air eventually formed from gases released by rocks and brought by comets. Every piece was a result of the galaxy's long process of building and recycling elements. Other planets in the solar system formed with different mixes of dust, rocks, and gas. The larger ones, like Jupiter and Saturn, grew quickly in the cold outer disk and kept thick atmospheres. Farther out, small icy bodies formed as comets and asteroids, moving slowly through space for billions of years. Planets are not alone. Around many, moons began to form, collecting the leftover material, spinning around planets rather than stars. Some moons became large and round, with their own rocky surfaces and sometimes ice or thin air. Smaller moons stayed as broken, lumpy rocks. These moons, too, are built from the remains of stars and clouds that lived and died before them. The forming of stars, planets, and moons is a cycle that repeats again and again throughout the galaxy. The process may be slow, taking longer than any living thing can see, but it is always at work, changing the Milky Way and filling it with more worlds. Even after a planet, moon, or comet forms, it can still pick up new material from space. Meteorites are small pieces that crash to the surface, sometimes bringing new elements or even water. All these parts can trace their beginnings to the heavy elements made in a giant star, scattered across the galaxy by an ancient explosion. Everywhere in the Milky Way, the story of clouds becoming stars and planets is a result of the galaxy's careful mixing and recycling of matter. Every part, from the smallest dust grain to the largest planet, owes its existence to the stars that came before and to the explosions that set their material free. When scientists study rocks, meteorites, and even the air on Earth, they can find tiny clues from this ancient cycle. Some atoms are very old, formed in the core of a giant star that exploded before the sun was born. Others are younger, made in the many generations of stars since. Each is a part of the larger story of the Milky Way's never-ending cycle. The Milky Way, with its billions of stars and even more planets, is a galaxy that has grown and changed because of how clouds, dust, and gravity work together. The elements for building solid ground, seas, and air were not present at the start, but with every star that lived and died, and with every explosion, the galaxy grew richer and more able to make new kinds of worlds. All around the galaxy, even now, new clouds are shrinking, getting denser, and beginning to build new stars and planets. The process never stops. Each new world might hold the right mix of elements for rocks, air, and water, and perhaps even for life. The same materials that traveled from the heart of a star to empty space, and from space to a planet, continue their journey even today. The cycle of stars and planets is the engine that shapes the Milky Way and brings new worlds into being, using the atoms first made in stars long ago. As new stars and planets kept appearing throughout the Milky Way, there was now something in the galaxy that had never existed before: the real possibility for life. Slowly, the special elements made inside giant stars and spread by their explosions became part of more and more worlds. These elements flowed through dust, collected in rocks, dissolved in water, and helped to make the air on young planets. Every time a star lived, died, and sent out its matter, the Milky Way grew richer with the atoms needed by living things. When you look at the world around you, the ground, the water, the plants, the animals, and even your own body, you are seeing the results of changes that began deep in the heart of a star. This story is not just about planets or rocks. It is also about life and all the things around us that are alive. Atoms inside you, such as the iron in your blood, the calcium in your bones, the oxygen in the air you breathe, and the carbon in each cell, all have their beginnings far away, formed at a time before Earth or even the Sun existed. Long ago, before any form of life could arise, the galaxy had to collect the right elements and then mix them in just the right ways. Every living thing, from the simplest cell to a giant tree or an animal, is built out of a small group of elements: carbon, oxygen, hydrogen, nitrogen, calcium, iron, sulfur, and just a few more. None of these were found floating free when the Milky Way first formed. Only after stars made them and threw them into space by exploding could these elements move into the next phase, becoming part of living worlds. Carbon is at the center of nearly everything alive. It joins with hydrogen, oxygen, and nitrogen to make the molecules found in plants, animals, people, and all living things. Without carbon, there could be no life on Earth or anywhere else. Carbon atoms are very flexible. They can bond with other atoms in endless ways, making simple or very complex shapes. This is how DNA, proteins, and cell walls are formed. The carbon in these parts of life once lived inside a star. Oxygen is just as important. It is needed for water, and it helps plants and animals breathe, meaning they use oxygen in their cells to make energy. The water in your body is joined by oxygen, which was built by stars before the planets even existed. Every drop of rain or bit of water you drink contains atoms that were once hidden far from Earth. Iron is essential for human blood and is carried around the body by special cells. It was formed by the fusion reactions at the very end of a giant star's life. That iron was expelled in a supernova and later collected as part of the rocks that became planets. In living bodies, iron helps move oxygen from lungs to every cell. Bones are made mostly of calcium. Calcium was also born in stars. It started as the simple elements, hydrogen and helium, which then became calcium only in the burning center of a massive star. Without these powerful stars, there would be no strong bones in any animal or person on Earth. Nitrogen, a big part of the air and important to all cells, was also first made in stars. Every time you take a breath, you are using an atom that traveled very far and was created long ago in a star's center. When Earth formed, it gathered atoms from all over the Milky Way. Some atoms came from giant explosions that had happened long before the Sun was born. Others drifted through space for millions or billions of years, mixing into the clouds that shaped the solar system. Over a very long time, these atoms, once trapped or floating free, became part of Earth's rocks, waters, and air. Plants grow by using carbon, hydrogen, and oxygen from the air and water. They collect these atoms through their leaves and roots, building their cells and energy from the sun. The food that animals eat also comes from these atoms. When you eat fruit or vegetables, the atoms making up those foods have their start as star-made elements. Even the tiniest worm or the thickest tree contains atoms made by stars. Animals, people, bacteria, and all forms of life use the same building blocks. Proteins, sugars, fats, and DNA are all built out of the elements made in stars. The long, complicated shapes that cells and tissues make are only possible because carbon can bond with many other atoms, and carbon could only get into plants and animals after giant stars made enough of it and sent it into space. Water, which covers much of Earth and is used by almost every living thing, is a molecule of 2 hydrogen atoms and 1 oxygen atom. The hydrogen was here since the very start of the universe. The oxygen came from stars. Only after the supernova explosions did enough oxygen join hydrogen to give the galaxy water. On young planets, water gathered in oceans, rivers, and lakes. Every cell in the body of a plant or animal is made of billions of molecules. Each molecule has a history that reaches back to a star's explosion. In your own body, most of the atoms were part of other things before you. Maybe a rock, maybe a cloud, maybe even another living thing millions of years ago. But before that, they were inside a star, taking part in the building of the galaxy. Life could not have begun without the elements mixed together, carried far and wide by the clouds of dust and gas from stars. Earth collected these elements over a long time, using them to build up everything on the planet's surface. Over billions of years, life used and reused the same atoms. When plants die, their atoms return to the soil. When animals die, the same happens. The cycle repeats, but the original source of these atoms was the ancient stars. Even today, scientists find proof that living things are linked to star-made elements. When they look at the special patterns of atoms in old rocks, in tree rings, or even in the shells of sea creatures, they see the fingerprints of the stars. By studying these atomic patterns, they can tell how much iron, oxygen, or carbon came from explosions long ago. The patterns in human blood and bones point to events in the galaxy that happened before Earth was formed. On distant planets, it is the same. If life exists elsewhere, it will also be made out of carbon, oxygen, hydrogen, and other star-borne elements. There is no other way. The only source of these, plus all other elements heavier than helium, is inside the burning centers of stars. The cycles of star birth and death are necessary for filling the galaxy with the tools needed to build life. Scientists also look at pieces of meteorites from space. These small rocks can be very old, sometimes older than Earth. They are made from the same dust spread by exploding stars. In these rocks, there are tiny grains that scientists can measure. They can see which elements are present, how they are arranged, and even how old the grains are. Some grains show strange or rare patterns that prove they were made in very old supernovas before the solar system appeared. The connection between living things and the stars is one of the strongest truths of nature. Nothing alive can exist without the special atoms and molecules created by stars. Everything that has ever lived or ever will live depends on the continued cycle of stars making elements, exploding, and sharing their matter across space. Inside the Milky Way, the same process is always at work. Clouds of gas and dust, filled with special elements from the past, collect together. They make new stars, new planets, and maybe new life. Each time a new planet forms from the dust, it takes with it the atoms needed for life. Each time life uses those atoms, it continues a story that started billions of years ago. Life on Earth is just one example. The process does not stop here. With every new star and every supernova, more special atoms are spread into the galaxy. The building blocks are always moving, always ready to become part of something new. The journey is long for each atom, but every path leads back to the stars. The Milky Way is filled with places where the cycle repeats. In some areas, stars are still forming, using the dust made from old explosions. Some clouds are bright and busy with new stars, others are quiet and dark, waiting for the right moment. But in every cloud, the right mix of elements makes new rounds of worlds and maybe new rounds of life. People carry inside them a record of the galaxy's history. The dust in bones, the iron in blood, the oxygen in every breath, and the carbon in DNA are all reminders of where we come from. These facts show that the story of each person is tied to the universe. We are made of the very same matter as the stars. Plants grow by connecting atoms of carbon and oxygen taken out of the air and water. The green color in leaves is helped by magnesium, another element made in stars. The wood in trees, the shells of clams, even the spark of a thought all rest on elements that were once hot and bright, parts of a star far away. Rocks and soil are also part of the cycle. The iron that colors red dirt or the calcium in chalk once formed in a star's center. When scientists measure the chemical patterns in rocks from across Earth, they see the tracks of the ancient explosions that made the galaxy's dust. When humans explore other planets, they find the same elements. Rovers on Mars have found iron, calcium, and other heavy atoms. Meteorites that fall to Earth from space have the same pattern of elements inside them. All planets use the same set of materials because the Milky Way mixes the dust and gas from old stars again and again. Life is possible only because the galaxy is full of the right building blocks. The combination of just a few elements made and scattered by stars allows living things to store energy, build strong bodies, and grow. Cells take the pieces, join them in the right order, and create everything from a tiny seed to a vast forest. From the air to the deepest ocean, everything shares the story that started with stars. Every day, new clouds are gathering the same materials. They will form new stars and new planets. Maybe, somewhere, they will make new life. Each thing that lives will use the old atoms, born in a star, just like every living thing on Earth. This chain means that the story of people, animals, trees, and all life is deeply linked to the stars. Every breath, every heartbeat, every step is only possible because the universe continues its work of making, breaking, and sharing the elements of life. As time goes forward, the Milky Way will keep changing. More stars will be born, more will die. More explosions will give out their matter. The dust of life will keep circling the galaxy, joining in new worlds, new rocks, and, when the right mix appears, in new living things. The connection between people and stars is not just from the past, but also a promise for the future. The Milky Way is a story written in atoms, and everyone is part of that story, made from the dust of old stars. As the Milky Way continued its cycle of star birth and death, the shapes and patterns of the galaxy itself were also changing. The huge explosion from the giant star did more than fill space with new elements. Its force had lasting effects across the Milky Way, helping to move, shape, and arrange the enormous clouds of gas and dust that filled the galaxy. The results of these changes are still present today, and they explain why the Milky Way looks the way it does. When a very large explosion sends out strong waves of energy, these waves travel through the galaxy for a long time. As the shock wave passes through clouds, it pushes and squeezes them. In some places, the wave forces the gas and dust together, creating thick areas where new stars can be formed. In other places, the wave pushes clouds away, making empty spaces with little or no gas. Both effects, the squeezing and the spreading out, help to shape the structure of the galaxy. These patterns are slow to appear. Each wave from an explosion moves for millions of years. Gravity continues to pull clouds toward the center of the Milky Way, while the energy from the explosion pushes some clouds further out. The combination of gravity and explosion shock waves spreads the star-made elements across the galaxy, but also helps create the beautiful curved arms that we see in pictures of the Milky Way. Sometimes the energy from an explosion is so great that it can break apart whole clouds. When this happens, stars that were born close together can be sent in different directions. As clouds rich with new elements are split or moved, the heavy materials from the supernova get mixed through much larger areas of the galaxy. As these clouds travel, some become stretched into long, thin shapes. Others are pressed tightly together and become the birthplaces of many new stars. These curved arms are called spiral arms. They are not made only by one explosion, but by the work of many explosions, gravity, and the slow turning of the galaxy itself. Every time a giant star dies in a powerful explosion, its shock wave marks the galaxy. The effects can be seen in how stars are gathered in some places and missing in others, forming the famous spiral pattern. Some areas look like bright knots because many stars were born close together after a shock wave hit a cloud. Other areas are dark and almost empty because the explosion pushed the clouds away. Inside the spiral arms, there are clusters of stars, thick dust clouds, and glowing gas. These places have lots of star-making activity, with new stars being born again and again. The explosions that happened before gave these regions the heavy elements they needed, so the stars here are often rich in iron, carbon, and oxygen. There are parts of the Milky Way where it looks like large, round, empty holes have been carved in the clouds. These holes are called bubbles or superbubbles. They are created when the force of many explosions or one very strong explosion pushes the gas far away from a point, making a low-density zone. In these clearings, you may find just a few stars or hardly any gas at all. The energy from the old supernova is still present, showing itself by the shape of space. The pushing and pulling of gas and dust has another effect. In some places, the explosion shock waves press clouds together so much that the gas becomes very dense. Gravity then takes over and helps the gas shrink until a group of new stars is born all at once. This is how clusters of stars appear, sometimes with hundreds or thousands of newborn stars. The cluster remains together for millions of years, but over time, the stars spread apart, pulled by gravity or pushed by new shock waves. The energy from giant explosions also stirs up the gas around them. The gas moves in big swirls, mixing the heavy elements with the lighter gases. This mixing gives every part of the galaxy a chance to gain the new elements made in stars, so even clouds far away can collect carbon, oxygen, and iron eventually. Because the energy keeps moving the gas, no part of the Milky Way stays the same forever. As more and more explosions take place over billions of years, the Milky Way's spiral arms become clearer. The arms are not made only of stars, but also of dust and clouds shaped by the explosions and gravity. New stars are always being formed in these arms, where the right elements and conditions come together. Sometimes, the powerful force from a supernova moves gas so far that it leaves the Milky Way entirely. This material becomes part of the halo of gases that surround the galaxy or is lost to intergalactic space. Even so, most of the heavy elements stay and mix into future generations of clouds, keeping the process of star and planet making going. The spiral shape of the Milky Way lets us see how the galaxy is always changing. The curved arms are signs of movement, of gas and dust being pushed, pulled, shaped, and filled with the building blocks from past explosions. The arms are brighter and denser than other parts of the galaxy because more stars are born there and more dust has gathered. The space between the spiral arms is not empty. There is still gas, dust, and many stars there, but in smaller amounts. The arms stand out because they have more of the material needed for stars and planets. The heavy elements made by past supernovae are spread everywhere, even between the arms, as the whole galaxy keeps spinning and mixing. Over long times, the spiral arms can move, break apart, or form new patterns, depending on how clouds, stars, and explosions interact. There can also be smaller arms, branches, or waves of gas inside the bigger spiral arms. Every pattern, every curve, every empty space holds the memory of what happened long ago, of an explosion that sent its energy across space and changed the Milky Way's shape. Scientists study the shape of the Milky Way by looking at stars, measuring their movements, and watching how gas and dust clouds move. With special telescopes, they can see through the dusty clouds and find places where the galaxy's structure has been changed by powerful blasts in the past. They find bubbles, holes, thick arms, and even the ashes of old explosions, all showing how the Milky Way has grown and been shaped by the death of stars. The spiral arms are not the only feature made by explosions. Gas rings, shells, and arcs have also appeared because of the way shock waves move through the clouds. Some of these patterns last for millions or even billions of years. Other shapes come and go quickly as clouds move, stars are born, new explosions occur, and the galaxy continues its constant changes. Every time a giant star explodes, it sends its energy outward, reaching farther into the Milky Way. The shock waves carry the fingerprints of the explosion, heavy elements, fast-moving particles, and heat. These shock waves cut paths through the clouds, moving matter into new shapes. The impact can be seen even now, as astronomers discover structures that only a powerful force could create. The way material is arranged after an explosion also matters for the future. Where the shock waves have compressed gas, the next stars are born from clouds already rich in heavy elements. These new stars likely have planets built from material left by the old explosion. Where the shock waves have cleared space, light and radiation can travel farther and other stars may shine more brightly. Astronomers use models to study how the Milky Way changes across time. They look at how explosions, gravity, gas, and the galaxy's own spinning work together. These studies show that the combination of explosions and gravity creates spiral arms, bubbles, and clusters. The places where past explosions were strongest usually line up with the places where the structures in the galaxy are brightest and most active. Sometimes, multiple explosions happen close to each other and around the same time. When this takes place, their shock waves meet and push the gas even harder, creating superstructures that can stretch across huge distances. Whole walls or shells of gas appear, dividing the Milky Way into different regions, each with its own mix of matter and history. The Milky Way continues to feel the effects of ancient explosions. Even billions of years after a supernova, its dust, elements, and shapes are still present. The spiral arms hold stars and clouds born from the first building blocks. The clusters help us see where the flashes of birth and death have left their marks. The holes and bubbles make the galaxy full of patterns, showing that change and energy have always been a part of the Milky Way's story. Within every bright group of stars, within every thick dust cloud, there is a memory of explosions past. The new stars shine from gas that was once thrown outward by a giant star's last act. Planets form from dust that spiraled through shockwaves before it gathered into worlds. Without the movement, mixing and shaping by energy from star deaths, the Milky Way would still be simple, without spiral arms, star clusters, or the beautiful clouds we see through telescopes. The work of shaping the Milky Way never stops. With every generation of stars, new explosions send fresh shockwaves across the galaxy. New holes appear, new clusters form, spiral arms twist or grow, and the mixture of dust and gas gets richer with the building blocks for planets and life. All the light and color we see from our place in the galaxy is proof of this never-ending process. When you look up at the sky and see the Milky Way stretching across the dark, you are seeing the result of all these events. The patterns are still changing, still being molded by the push of shockwaves and the pull of gravity. The next steps in the Milky Way's history will keep adding to these patterns. The energy, elements and clouds born in ancient explosions will continue to shape the arms, the gaps, and the bright centers where future stars and planets will develop. Even as the galaxy turns, the marks left by old supernovae remain, guiding and changing the Milky Way's form. The story of the Milky Way's changing shape is a story of movement, energy, and connection. Every star, planet, and cloud feels the effects of the powerful blasts that happened long ago. These changes help make the galaxy able to support new stars, new planets, and all the possibilities that come with them. The spiral arms, the clusters, and the empty holes are all written by the energy from the past, creating the map by which the future of the galaxy will unfold. The Milky Way's structure, filled with spiral arms, clouds, and star clusters, still holds the signs of many powerful explosions that shaped the galaxy over billions of years. Everywhere you look, the evidence remains in the way stars and gas are arranged. But how do we know what happened so long ago? How do scientists learn about the ancient explosions and the birth of the elements that made planets and life possible? Researchers must work like detectives to understand these old events. They cannot visit the past, so they look for clues left behind. Their main tools are telescopes, spacecraft, computers, and careful measurements. By observing light, studying patterns, and analyzing materials, scientists gather pieces of a puzzle about the galaxy's history and its biggest events. One of the most important clues comes from the light that reaches us from distant parts of the Milky Way. Every kind of element, such as hydrogen, helium, oxygen, carbon, and iron, gives off or absorbs light in a unique way. Even the tiniest cloud or farthest star leaves a signature in its light. When scientists look through special telescopes and break that light into colors, they see lines or patterns. These patterns tell what is inside the cloud or star. By collecting this information, researchers can map where certain elements exist in the galaxy. For example, a strong presence of oxygen or iron in a cloud means that explosions from giant stars have touched that area in the past. Sometimes scientists find clouds or stars that are rich in carbon, or others with lots of heavy metals. Each discovery helps to build a picture of how elements have been spread by ancient explosions. Not all clues are from light. Sometimes broken pieces from space like meteorites fall to Earth. These small rocks often carry atoms and minerals made outside our solar system. Scientists carefully study these visitors using microscopes and special machines that can count the types of atoms inside them. They often find rare grains that were made in giant star explosions long before the solar system formed. These grains are much older than any planet or moon. By examining these ancient grains, scientists learn what kind of explosion produced them. Some grains show that they formed in intense heat, others in very high pressure, and some contain patterns of elements found only in supernova. Each grain helps to tell the story of what happened in the Milky Way a long time ago. Computers are important for understanding the past as well. Scientists use them to make models of explosions, gas clouds, and the movement of galaxies. These models use the laws of physics and information about the elements to replay possible events from the galaxy's history. If the models can make the same patterns of light, elements, and shapes that we see in space, then it means the models may be right. Sometimes, telescopes catch events that are still happening today. There are parts of the Milky Way where new supernovae explode, sending light and energy out for us to see. By watching these new explosions, scientists learn how old explosions might have worked. They can measure the speed of material flying through space, the temperature of the gas, and how long the light from the explosion lasts. With this information, they can understand the power of ancient events. Some of the strongest clues about past explosions come from the way stars and gas are arranged in the Milky Way. When scientists study the galaxy, they see bubbles, holes, and arcs in the clouds of gas. These shapes appear when explosions push gas away or squeeze it tightly together. By measuring how wide or deep a bubble is, and by counting how much heavy material it contains, researchers can tell if a giant explosion happened there millions or even billions of years ago. The patterns in star clusters are also important. Sometimes, a group of stars all have about the same amount of heavy elements in them. This means they probably formed together from the same cloud, which was likely touched by the dust and energy from an explosion. If one area has many stars with lots of iron, scientists think a supernova added extra iron to that region before the stars formed. Telescopes in space help scientists study the Milky Way without the limits of Earth's atmosphere. These telescopes collect X-rays, ultraviolet light, and even invisible waves, which carry unique signatures of the elements created in explosions. With these tools, scientists look deep into space and see the remains of ancient supernovae, large, bright clouds full of special elements that are still expanding today. Researchers also look at the ages of stars. Some very old stars have few heavy elements, which means they were born before many supernovae had exploded. Newer stars almost always have more iron, carbon, and oxygen, showing that the galaxy grew richer in these elements over time. By measuring the light from many stars, scientists build a timeline of how explosions slowly change the Milky Way. Rocks on Earth carry clues too. Some rocks contain special versions of atoms called isotopes. The only way for these isotopes to exist is through the energy of a supernova. When scientists study deep layers of Earth's ground, sometimes they find traces of old supernova events that happened nearby in space. These isotopes could have landed on Earth after traveling across space for millions of years. Scientists measure the speed and movement of gas in the Milky Way, sometimes seeing streams or flows that follow the path of an old shock wave. These flows can move at hundreds of kilometers per second. When they pass through other clouds, they can start new star formation, just like they did in the galaxy's past. By tracking these movements, scientists see the fingerprints of past explosions shaping the galaxy now. Even the solar system carries signs from long ago. Some isotopes found in meteorites and old rocks show that just before the sun was born, a supernova exploded near the cloud that formed our solar system. The supernova's shockwave may have helped push the cloud to collapse and begin the process of forming the sun and planets. Without that event, the solar system might not have formed at the time it did. To discover more, scientists often look for patterns in the way groups of stars move together. If a group of young stars all travels in the same direction and has similar elements, it is likely they formed from material shaped by an explosion. Sometimes a careful study of the star's positions and speeds can even point to the direction and location of supernova that happened millions of years ago. Large computers can store and process huge sets of data, comparing observations from telescopes, spacecraft, and even ground-based labs. By putting together many small clues, scientists can build pictures of how much iron or carbon was spread during each supernova. These pictures help explain which areas of the Milky Way became rich in heavy elements first, and which areas remained simple and poor in elements for much longer. Still, there is mystery in much of what scientists find. Some explosions seem too powerful or too rich in certain elements to match models made on computers. Some clouds have strange mixes of elements that do not fit what is expected from any known explosion. These puzzles keep researchers searching for more information. In some parts of space, scientists find clouds with more of one element than usual. For example, there might be a cloud high in oxygen but low in iron or carbon. This tells scientists about the kind of star that exploded. Some very large stars mostly make oxygen before they die, while others make more iron. By matching patterns in the elements, scientists build a map of many different past explosions. Sometimes, the way elements are spread in the Milky Way shows that explosions must have happened together, close in time and space, to make the observed pattern. These chains of supernovae push and pull clouds in special ways, creating large holes or waves that only a group of explosions can shape. The arrangement of these holes and waves is a big clue to how the galaxy has changed and moved. Scientists also learn from studying other galaxies. When a neighbor galaxy shows similar patterns of elements, star clusters or bubbles, scientists can compare them with the Milky Way. By finding the same clues in different places, they understand that the rules of star birth, death, and explosion work everywhere in the universe, not just here. By studying the remains of ancient explosions, scientists uncover not only the history of the Milky Way, but also what is normal and what is unusual in the universe. Every measurement, every sample, every image helps to solve the mystery of how the galaxy became full of stars, planets, and life. All of these discoveries connect back to us. When we know how ancient explosions filled the Milky Way with iron for our blood, carbon for our cells, oxygen for our air, and calcium for our bones, we know more about our own story. Every stone, every drop of water, and every plant shares the same past. The galaxy's past is written in light and matter. Scientists read this story using every tool they can. The more they learn from the stars, the more they can understand how galaxies form and change over time. Scientists continue to look for more clues. New telescopes and missions gather better data every year. As their knowledge grows, the story of the Milky Way's powerful explosions comes into better focus. Still, many things remain hidden, waiting to be discovered in the light of the stars or the dust that travels between them. The search for answers is ongoing, bringing together people from all over the world. Each new discovery opens a new path and sometimes brings new questions. With each step forward, we learn more about the ancient events that made everything in the Milky Way possible, including our own world and our own bodies. Even after all these years, the mystery of the Milky Way's powerful explosions and the spread of the elements continues. As scientists study, they find new connections between the life and death of stars, the building of planets, and the story of life itself. The clues from long ago are still all around us, guiding our search to better understand where we came from and how the galaxy took its shape. The search for clues about ancient explosions continues every day. scientists look deep into space to understand how the Milky Way became a place filled with stars, planets, and life. Each discovery brings new understanding, and each piece of information about old supernovae and the spread of elements shows the importance of these events for everything we see and know. The huge explosion of a giant star did much more than change its surroundings. It created the conditions for new worlds. Without that powerful event, the Milky Way would have stayed a quiet galaxy, full of only simple gases. There would have been no iron, no oxygen, no carbon, no calcium, and no other heavy elements needed for rocks, water, and living things. Because of these old explosions, the galaxy turned into a place where new stars could form with disks of dust and gas that held all the ingredients for planets and, later, for life. Every part of Earth shows this story. From the solid ground to the water in oceans and the air above, everything is built from the building blocks made in stars. Iron forms the core of Earth and is found in many rocks. Oxygen and hydrogen, which make water, were sent out by stars and gathered on our planet. The carbon in plants and animals also comes from space, first created deep inside a star. When a person walks outside and sees a tree, a river, or a hill, or looks up and sees the moon and stars, they are seeing pieces of very old events. Each of these things needed the right elements, and each element was born in the heart of a star and then released in a powerful explosion. Every breath, every heartbeat, every step on the ground connects to a larger story that started long before humans or even Earth existed. Human bodies are full of these special atoms. Blood uses iron to carry oxygen. Bones are built from calcium. The cells in a heart, the fibers in a muscle, the materials for hair and skin all depend on elements that first appeared after a star exploded. People are the living proof that explosions in galaxies make life possible. Life on Earth is made from only a small group of elements, but these are enough for a great variety of living things: trees, flowers, animals, insects, and people. Every living thing shares the same set of atoms: carbon, oxygen, hydrogen, nitrogen, calcium, iron, and more. All of these first came from ancient stars. The cycle of stars living, dying, and giving their matter to space is the reason living things can exist at all. When scientists say we are made of star stuff, they are speaking a truth that links all life to the universe. This connection goes beyond Earth. It is found in every place where stars, planets, and water exist. The same processes that filled the Milky Way can fill other galaxies. The same rules of physics and chemistry, the same making and spreading of elements, can lead to new worlds everywhere. This story teaches that everything is connected. The galaxy is not just a place for stars to shine. It is a system where energy and matter move, where simple things become complex, and where change shapes the future for all time. The explosion of one giant star may seem far away and long ago, but its effect reaches through time and space to every person, every plant, every planet. Planets could not have formed from only hydrogen and helium. For solid planets, for seas, for air, and for life, the galaxy needed heavy elements. These came only from inside stars, freed during their deaths. The careful work of millions and millions of years was necessary to gather all the needed materials. Even now, every new star and planet begins with the dust and atoms from many earlier generations of stars. The Milky Way's shape, with its bright arms full of new stars, is only possible because of the way explosions moved gas and dust. Every bump, every gap, every cluster is a sign of these past events. Without these movements and changes, the galaxy would look empty, with only a faint cloud of gas. Instead, it is a place of bright regions, dark spaces, and beautiful spirals. Just as the galaxy depends on these processes, so does the future. The Sun, Earth's own star, will not live forever. In many billions of years it will change, and the atoms in and around it will move on to join new worlds. Some will become part of new planets, some part of new stars. The cycle will continue, and the materials inside every one of us could one day be part of something completely different. The study of these old explosions gives scientists more than answers about the past. It gives ideas about what is needed for life and planets to appear anywhere in the universe. If another galaxy has the same kinds of stars, the same kinds of explosions, and the same mixing of elements, it too can develop new worlds and maybe life. This understanding brings a sense of connection not only in space but also across time. The atoms in each person's body have traveled, been changed, and reused through nearly endless cycles. They have moved from stars to clouds to planets, from rocks to water, and now form life. This never-ending recycling links everyone to the very first stars, to every explosion, and to the wider story of the universe. Scientists keep searching for more clues. They look for the signals of old supernovae, study the oldest metals in Earth's rocks, and watch stars aging and changing. Everything they find makes the picture of the Milky Way clearer. Each question brings new discoveries, and each discovery is a step closer to understanding how the universe works. This story is not just for science. It shapes how people see themselves and the world. When a person learns that their body, their home, their food, and their air all started in stars, it brings a new respect for the galaxy and the universe. It shows how precious and rare life is, and why every person is connected to the same great story. The future of the Milky Way will depend on the same rules that built the past. New stars will be born as clouds of gas and dust gather and shrink. Other stars will grow old and explode, sending fresh elements out. The spiral arms will turn, new worlds will appear, and the cycle will repeat. Somewhere, after millions or billions of years, more planets may become homes to life. The galaxy's story is one of patience. Change happens very slowly, but the results are powerful. From the making of heavy elements in a star's heart, to the spreading of dust through an explosion, to the birth of each new world, the Milky Way is always growing and changing. It gives everyone a place, and it holds the memory of everything that has ever happened here. People are just one part of this bigger journey. The same story is told in every star's burning, every planet's path, every atom's movement. When scientists look into space, they are searching for their own beginnings. When people look up at the night sky, they are seeing the future and the past at once. The Milky Way will continue spinning, growing, and changing. The forces that shape it, gravity, energy, explosions, and the movement of atoms, work everywhere, not just here. Every new supernova writes another chapter, mixing more dust, making more worlds, perhaps leading to new life. The cycle of life, death, and rebirth is not limited to Earth. What happens here happens throughout the galaxy and even in other galaxies. This idea brings hope and wonder. It encourages people to keep exploring, to keep learning, and to value the special chance they have to be a part of the universe. Scientists know there are still mysteries left to solve. How did that first giant star become so massive? Why was the explosion so powerful? How exactly did the shockwaves change the arms of the Milky Way? Which stars and which clouds made the elements in each person's body? The search for these answers is ongoing, and every generation adds new knowledge. People can feel awe at knowing their own atoms have traveled across space and time, once part of forgotten stars. Every living thing, every stone, every cloud follows the same big cycle. This is a story of belonging, of being made from the galaxy itself. tied to every part of creation. When a child looks at the stars, they are seeing family. The light in their eyes has traveled for millions or billions of years. The dust that settles on their hands was formed in the same kinds of stars that made them. This connection runs deeper than any history, any border, or any difference. The Milky Way's story is not finished. It is still writing new events, shaping new worlds, and preparing places for life to begin again. Each explosion, each movement of dust, each new star or planet adds a fresh page. Even now, as technology grows and people learn more about space, the basic truth remains. Everything is part of the galaxy's big picture. The meaning of the ancient explosion at the center of this story is not only scientific, but also personal. It shows that the universe is filled with cycles, with opportunities for new beginnings, and with connections that join everything together. It invites everyone to pause, to think, and to imagine their own place in the grand story of the Milky Way. In the end, the galaxy is not just a giant group of stars or a faraway place in the sky. It is the source of all matter, the place where life is possible, and the link between past and future. It is a story about energy changing form, about atoms moving and joining, about stars living and dying, and about the growth of worlds and life. Every step, every discovery, every life is a part of this long journey. No matter where someone is or how much they know, they share in the rich, ongoing story of the Milky Way, the galaxy shaped by the life and death of stars, the growing of elements, the forming of planets, and most of all, by the miracle of change and connection.